My name is Felix Gröbert. I'm from Bochum, Germany, the Ruhr University of Bochum, and I did this work together with Christoph Wegener, who's also at the chair for data and network security in Bochum. And we have 50 minutes time for this talk, and if you have any questions, just raise your hands. I will try to reverse some time in the end of the talk to answer further questions. And I'm also hanging around the conference till Saturday morning, till the brunch. And you can question me anytime. Also, if you want to send me an email, my email is displayed over there. So this talk is about a proof of concept attack we did on a real-world deployed SmartCard-secured online banking solution. And first of all, I'd like to thank my supporting colleagues, Christoph Wegener and Jörg Schwenk, for supporting this work and enabling me to do this work. It's about a real-world bug, so it's kind of difficult here to talk about this bug, and because it had a real-world deployment, and so this yields a real-world threat to the deployment. And because of this, we spoke with the producer and the vendor of the product, and they collaborated with us to issue a patch, and people can now apply this patch. So I think it's okay to speak about these things we have done. First of all, I like to present you some solutions I encountered during my life for online banking. These solutions generally authenticate transactions which are done using online banking. You see transaction numbers, one-time passwords, several sheets of one-time passwords. You see a mobile phone, which is a newer solution to transmit one-time passwords. You also see a one-time password generator and several software products which build upon smart cards and smart card readers. So one-time passwords were first tackled by phishing in it came up in really big and grew really big in 2003. And one-time passwords were used to authenticate online transactions using at first the login and a login password, but also the possession of the sheet where all the one-time passwords were pinned upon. Then you had one-time password generators, which were generally time-bound, to which bound the token it generated to a certain time frame. And in order to tackle these kind of online banking solutions, you had to do adaptive phishing, man-in-the-middle phishing, in order to interactively sniff the one-time password from the victim and then in real time transmit it to the online banking site where it was used to conduct a transaction to a money mule or something else. So here you also have a two-factor or a three-factor authorization. You at first have to have the possession of the device itself. Then you insert your credit card into the device, and you also have the authentication factor of the knowledge, where you have to know the login and the login password to conduct the to enter the online banking site. Third, you have seen software clients which build upon smart card readers to conduct online banking, and they were publicly tackled by code manipulation by Hanno Langweg in 2007. And software clients use smart cards readers to sign transaction details, and the signature is transmitted along the transaction in order to authenticate it. Then you have the GSM transfer of one-time passwords, where you enter a transaction into your online banking account, and you get a short message where you receive your one-time password, and you receive this one-time password on your PDA or your mobile phone, and you enter it into your online banking site, and then the transaction is authenticated. This heavily relies on the security of the GSM, and probably I'm kind of looking in the future here. Maybe GSM will break in 2011, but just ask Carsten Noel, who has a talk about GSM security tomorrow in the morning, and maybe he can tell you a more certain date for the fall of GSM security. 2010. So, where are we? You see this communication diagram where the user controls the browser over user interface and the browser communicates with the banking site over SSL. So an adversary has the possibility to tackle either the user or the operating system. He can target the user by targeted phishing attacks where he tricks and scams the user into submitting otherwise secret information, or the adversary may use the malware to technically target the user and install malware on the operating system, and thereby change transaction details and stuff like that. So, if you're doing smart card-based online banking, you have to keep in mind that you generally use some kind of software which is installed on your system, and this software interfaces a smart card reader. You can differentiate between several classes of smart card readers. For example, a device with security class 1 only doesn't have a trusted input or a trusted output. It's just a USB stick or otherwise connected device which contains a smart card and receives data, signs it, and sends it back. Devices with security class 2 have a trusted input, like a small pin pad, where you can enter your personal identification number, and here you aren't able to monitor the pin which is entered on the computer keyboard, but you don't see what you sign, and here you aren't sure what you are signing by entering the pin into the device. Devices with security class 3 have a trusted input, like a small display, and a trusted output. If you use a security class 3 device, the security depends on the information which is displayed on the screen. But the security also depends on how much information is displayable on the embedded screen, because it's usually really small, and you can just display some 30 digits there and aren't able to display a lot of information. So what is commonly done is that the display contains, for example, a hash of a PDF which you're about to sign, and you can't really compute a MD5 or SHA-1 hash in your head, so you also don't see what you sign, and thereby you can be the information which is signed is maybe manipulated. So coming to our proof of concept attack and the audit we did, we looked at the USB class 1 smart card reader and containing a smart card. It also contained the USB stick you see there, contained a USB mass storage device with pre-installed hardened applications. There are different deployed revisions of this device for several banks, and the solution we looked at is targeted at the Commerzbank business clients, and they have the need of signing several transactions with one digital signature. And in Germany, you have this law that a digital signature is equal to a normal signature. So you have the possibility to sign transactions in a mass scale and commit them over a large scale. So that was a need for those customers to conduct one signature. You can't really tell a CEO to enter his or her PIN like 1,000 times for each transaction, but you want to sign one batch job of transactions. The solution also had a very small deployment, and which is something we learned from talking to the guys. And compared to a standard class 1 reader, the complexity to attack the system is generally higher than attacking a normal class 1 reader, because you have this hardened applications, but I will come to this back later, how hardened they really are. And after our disclosure of the vulnerabilities, the producer issued a software update. So we only analyzed one device and one revision, namely the one from April this year. And we also had the user ID you have for entering the online banking site, and a password and the password for using the inserted card. If you plug this USB stick in, you find a read-only CD drive mounted, and the solution on the CD drive includes several applications. One is an application wizard, which sets up an application environment, an update client, and a modified Firefox. As I told you, the system has some kind of hardening in it. As it's built up upon a class 1 reader, it also needs this kind of hardening. For example, it has partial code integrity checks. I will come to this back later. And the updates to a system may be enforced, otherwise the solution won't work. So you have to apply an update in order to conduct your internet banking. And you also have good control of temporary files. If you, for example, take this USB stick and plug it into a public internet terminal, the USB stick and the applications embedded on it take care of removing temporary files. So we think this increases privacy and is generally a good thing. And also you have the read-only media. It's not always mounted on the desktop. So if you think about the scenario where you have a malware running on a system which looks for installed applications and then statically patches these applications to modify its code, you don't have this attack scenario here because, for example, the stick isn't always mounted in a usage environment, and it's a read-only media. In order to replace the installed applications, you have to go to the path of the update client, which is also using cryptography to sign the applications, but we didn't look at the update client. So if you log in and want to make a transaction, it looks like this, German interface, and you enter your transaction details, target bank account and stuff like that, and then you click on the on the button on the down right, and then it pops up a Java application which speaks to the smart card, and the Java application takes care of signing the data and delivering it back to the web application of the bank. As I told you, you have several processes installed. For example, the application wizard, which takes care of setting up the environment. The application wizard relaunches itself, and copies itself over into the temporary directory under the user's home directory, and then launches the update client, which has a return code, whether there's an update or whether there's a mandatory update. And if the return code is sufficient for the app visit launches the modified Firefox CPWD, which is then used by the browser. And when the browser quits the Firefox, AppVisit launches another executable, removex, which deletes temporary files. So the vulnerabilities we found is divided into classes. The first class is the concept of the solutions, because it uses a class 1 reader due to the usage environment with the mass signatures. The concept is generally fraudulent. With the class 1 reader, you have a general problem of not seeing what you sign, and if you don't see what you sign, you have a problem. Secondary vulnerabilities are the Firefox versions. As you might know, the Firefox 1.5 is quite old. And for example, it contains several features like the null-byte SSL bug. It has some domain restrictions where you can browse only on the banking site, and you can circumvent this domain restriction. For example, if the application runs in an internet kiosk where you aren't supposed to launch or browse on other sites, you can circumvent this domain restrictions by clicking on help and then about Firefox. And it contains obsolete CAs, for example, CAs which are signed by MD5. And this introduces, of course, the bug which was found by Lenstra. And also the Firefox doesn't have certificate verification lists, but this is generally not a problem as the solution contains the update mechanism. The code integrity checks aren't very sufficient, as I will show later. And it contains several debug strings and messages which are outputted by output debug strings, which were quite helpful while reversing the solution. The hardening is done by 2 checks. The first check is a specific thread in the Firefox.exe. It checks the addresses of certain vital Firefox functions, which are namely SSL underscore and PR underscore read, and several other functions which are substantial for the communication with the bank. And every 42 seconds, a special function in DLL is executed, where there is a check whether Firefox extensions are installed or whether there's a debugger attached to the binary. Actually, our first attempt to modify transaction was to install a Firefox extension like GreaseMonkey, where you can modify site contents and also modify the behavior of a website. But the check if there's an XPI installed rendered this attack path unuseful. And also the timing is done using syscalls like time and sleep. So if you can hook those calls and disable those calls, or create a wormhole by setting the time to a constant value, the 2 seconds check or the 42 second check won't be something different. So this time will be constant, and you can thereby disable those checks. The solution also has the vulnerability every class 1 reader brings, namely that you can monitor keystrokes on the personal computer's keyboard, and can easily perform those with the function. So our main attack, we wanted to show that it is possible to modify transaction without the author knowing. So we had the idea of different attack vectors which we could take. At first, you can target the operating system layer, where you modify video memory or input done over the keyboard. You can take the path over the Firefox functions for displaying content. And for example, Firefox functions for input and output. And you can go over the web application layer, where you can introduce arbitrary interactive web content by inserting it into HTTPS. And we took a mixed approach of using an attack over the application layer and also the web layer, where we had the flexibility of using JavaScript to modify input and output and modify the display of the site contents. Of course, we had to at first use the several methods on the application layer where we disabled certain checks and injected JavaScript into the HTTPS screen. In our first stage, we patch the function isDebugger present. Then we hook the function which is mandatory for the execution of JavaScript inside Firefox, which is a JS-evaluate-UC script for principles. And then we override a static function inside the web application, which is the JavaScript function OpenHead, which is always there, and we override it to load our arbitrary malicious JavaScript. So if you remember the communication diagram, the malware, the scenario which we are assuming is the man-in-the-box scenario, where we have a malware which sits between the user and the installed application, and we control everything the user does over the user interface with the application, and we control everything which goes to the USB stick, which is to be signed, and we also control the signature which is coming back to the application. So, for example, we want to return isDebugger present always no, or we want to modify SSL traffic which comes from the bank to the application. This is done by function hooking. Hooking is a fairly old technique of altering function input or output, and several methods exist. And we took the method of inline hooking because import address table or system service descriptor table redirection or hooking is not a runtime approach, but a more static approach. And we looked at the function entry point and modified the code there. If you do inline hooking, it requires a disassembly, though, in most cases. And what you do is that you put a jump at the beginning of the function entry point, and this jump is then processed in the code caves. But you also need the disassembly of the first bytes of the function entry point, which needs to be executed at the hooking point where you jump to. You can also place, instead of a jump, place an interrupt at the beginning of the function entry point and process the data in the debugger, which is the path we went for the proof of concept, because we didn't want to produce a real-world working malware, but instead we wanted to show that the concept is possible. And we first evaluated the Debugger hooking DLL and AP, which is quite good, but we came to the point in the project where it has to be finished and not much time is left. So we went with the solution of using the immunity debugger. And this is done using Python. And I'm writing on the slide that this attack code is obsolete, so we think it's okay to show it here. And what this code does is that it, in the first two lines, it presents, it uses the immunity debugger function of get address, where it pulls the address of the isDebugger present function, and then it overwrites at the address of isDebugger present an assembly which generally XORs the return value and XORs the EAX register and then returns, so the return value will always be 0. Then we register an immunity debugger hook, which is in the lines 3 to 5. This hook is placed on the static address of JS evaluate UC script for principals. And each time this function is called from this point, the Python method run will be executed, which gets first the address of our to be modified JavaScript string from the register EDI and reads it in as a wide string, which is because of the Unicode encoding of the string. Then it checks whether the string is contains the OpenHead function. So we are sure to overwrite only the one JavaScript function which is static and which is not mandatory for usage of the web application. Then we overwrite this string with some loading of the external JavaScript, where it just writes that the malicious JavaScript should be loaded from an external server. We add some null bytes and zero up the rest of the string and log that the JavaScript has been patched. So the function help, which you might see in the bottom of the slide, the function OpenHelp is overwritten by the to load the malicious JavaScript. This malicious JavaScript works the way that it first waits for the window on load event, which is triggered when the page has been rendered. Then the malicious JavaScript checks whether the location is a transaction form, where you enter the transaction details and things like target account and stuff like that. If it is, it registers an event listener for the button where you click on to send your transaction to the banking site. It then saves the original input, like the bank account number, where it originally should be, where the money should originally go to. It substitutes this bank account, for example, with the malicious input, and visually hides the modification from the user, and submits the malicious transaction to the web server. If the page contents isn't the transaction form, we don't want that the user raises attention, and we search for text which contains our modified and manipulated input, and substitute this text with the original text, so the user won't see any changes to the original behavior. So we did this with the Verwendungszweck, which is German for transaction details. You see the Verwendungszweck is test here. We click on the button to sign the transaction. The transaction has been signed. The transaction number is L9FL. The transaction detail is test. And if we look at the transaction overview in a similar page, we see that the transaction detail is still test, and the user doesn't gain any attention. So this is a communication diagram for this attack. We could also have modified the balance, because if you're doing fraud with online banking malware, you're generally modifying a transaction and raising the amount of money which is triggered by this transaction. For example, if you want to send 50 euros to your aunt, but the malware modifies it to 500 euros to a money mule, your balance in the end will be, well, 450 euros off, right? So common malware like URL zone, for example, also detects the current balance, which is displayed in the summary of the transaction overview, and adjust this balance by adding 450 euros, for example, to this balance. But this isn't something we implemented because, well, we just did the proof of concept. If I switch off the modification of the web application, the transaction detail now is named manipulated detail. This is the JavaScript attack code. It's well, self-explanatory. Still some time left, so I'll just walk through it. At first, it checks whether the document location confirms to an input for a form where you enter your transaction. It gets the element of the button. It gets the it registers an event for on click to this button that the function which is in the add element event listener will be executed. This function just gets the original value which is inputted by the user and saves it to a database, sets the new value, and also adjusted the CSS style to color white. So you have this input text field which contains a white background and a dark text, and now the foreground dark text will be overwritten. The value for the color of the dark text will be overwritten, so you have white text on white background, and the user doesn't see the manipulated transaction details while the next page is loading. If we aren't on an input of a transaction, we evaluate all text nodes and use a regular expression to substitute all text nodes where the manipulated string is contained, and substitute this manipulated string with the original string. Okay, our attack method has some drawbacks. As I already told you, real-world malware author would use binary patching instead of using a debugger. And also, we currently use cookies as a persistent or non-persistent storage in the browser. So if you plug out your stick and plug it back in, your changes will be lost. And so we could use some better data storage there. So, but we think it's a small effort to make those changes to the solution, and real-world malware could be created easily. But as the deployment of this online banking solutions is only like 1,000 units, this wouldn't be profitable for a malware author, and he also, or she has to also do all this kind of reversing, so the malware author will more or less go for the easier targets and attack the easier targets, so it doesn't seem profitable. Countermeasures for the attack may be the usage of a picture to display the transaction details and the transaction overview. And in this case, we would have to use image recognition or some kind of OCR to get the textual representation of the data. And like image recognition Also, the anti-reversing techniques are kind of an arms race because you just need to adapt to the next defenses or attacks, and you get into the kinds of arms race. Yeah, better code integrity checks would be very, very good to further secure the solution, and also code obfuscation. Well, like, yeah. Also, the usage of class 3 reader might also mitigate the issue, but as I also already told you, the usage environment requires mass signatures, and also a class 3 reader is quite expensive. Coming to the conclusion, we say that even if the application is professionally hardened, any malware can still manipulate input and output because it's built upon the class 1 reader, and therefore the security model which is underlying the solution is always information theoretically manipulated using malware. So it's a failure of the concept. And hardening as a countermeasure is only an arms race, and in our opinion, it's an arms race in which most vendors currently lag behind. And if you take into account the usage environment, you might consider that using a trusted in and output, namely out-of-band in and output, is required for this usage environment. But this is a discussion where you have to take into account several business cases and business decisions. And yeah, a good proof of concept for a class 3 reader or class reader is the Zurich trusted information channel. And also there are other class 3 readers which are might be used for a solution here. So, are there any open questions?
Any idea how similar this particular example is to the other banks that deploy similar measures?
I repeat the question. You are asking whether the banks I mentioned in the beginning of the talk have the same kind of vulnerabilities and problems?
Similar problems, vulnerability, sure.
Yeah, we just look at this one revision for this one bank, and I don't feel very comfortable talking about the other banks, so I can't answer this question.
What about the install base? There was about 1,000 for this particular application. The other banks, any idea on the install base there?
For the other banks and companies, it is used partly as an in-house tool, not for customers, and therefore it isn't exposed to an attack scenario like this one. But as far as I know, the whole solution is more targeted at corporate environments. Where you don't expect like running man-in-the-middle infected boxes and malware-infected boxes, which are, well, yeah. Okay. If there aren't any further questions, you can also mail me or talk to me later. Thanks.